Okay, let's dive into approximate indeterminate solutions. So at this point in the history of structural engineering, it really isn't useful, maybe useful is the wrong word, necessary to solve a lot of indeterminate analysis by hand. Honestly, the structural software that's out there is good enough and reliable enough by quite a ways that anything that we used to do indeterminate by hand just is done so much faster and so much more accurately in finite element software. However, with that said, it doesn't take much to completely screw up a finite element analysis just by the misclick of a button or really a misunderstanding of what the software is doing. I would say at this point the software is good enough and accurate enough that if we know how to use it, we're going to get the results that we want. So with that said, having a way to quickly validate or even not so quickly validate our FEA models is really valuable. Also, if we have maybe a somewhat complex problem we're solving, we can bound the upper and lower bound of a solution and then say to ourselves as we get more refined into it that we're honing in on a true solution. Okay, so some of the whys: quick estimate of forces and moments, check on more complex analysis. So the first thing that I want to talk about is just shifting the moment diagram. So if I have a simple span beam, point load, my moment diagram looks like that. If I shift it up, my moment diagram looks like that, which is consistent with what it looks like in reality. So here I have a moment diagram like this, fixed end condition for the same thing, I shift it up. If I look at this here, same deal, I can take this diagram and shift it upward. You notice my moment is WL squared over 8. If I add the WL squared over 12 to over 24, it equals WL squared over 8. So it's a pretty simple thing to do, and it gives us the ability to say, okay, if I went from a beam like that to a statically indeterminate beam like this, I should expect a moment diagram of magnitude that has a relationship to this diagram. Okay, in concrete beams, we have what are known as the ACI coefficients. So as long as we meet certain span relationships and loading type criteria, we can come in here and use these coefficients to say, okay, the moment here, depending on if it's a column or a beam, is going to be WL squared over 16 or 24 if it's a beam. It's going to have a max positive moment, which in this case we're calling negative sign. And then a moment, or actually that's wrong, that should not have a negative. Anyway, then we have a moment at the face of the column, a moment at the midspan, and so forth and so on. And you can expand on this in ACI 318, but one of the things that starts to become apparent is if I change this coefficient based on what I believe my fixity of my ends are, I can start to get pretty good estimates of moment. Maybe not to the point that I want to hang my hat on it, but enough to say when I look at software, oh, those things correlate, they make sense, it looks like things are going the right way. Okay, next topic, brace frames. Sometimes we have frame configurations like I've shown here. If we want to say the brace only acts in tension, then this problem becomes statically determinate. Similarly, if we have maybe tube or wide flange braces, we can say, well, those until one of them buckles, those braces are going to share load equally. And that's a safe assumption. And again, a way to quickly in a model say, okay, well, if I have a story force of 100 kips, and that's going into two brace frames, and I have two compression or two braces that'll share the load. So I take 100 kips, split it in half to each frame, and then half again into the brace. I could say I should have a horizontal force going into that brace around 25 kips, and then do the math to increase that force because it's at an angle. So there's actually an example here that I've given you that you can walk through that, how I've done this. And really, one of the keys is dividing by the cosine of that angle so we can get the magnified force because it's at a slope, not just a horizontal shear. Okay, next method, moment frames using the portal method. Naturally, it's great to run this in a finite element software, and this building was designed that way. But if I wanted to check the moments in some of those members and make sure the software is running properly, or maybe even more appropriately said that I'm using the software properly, I can come in here and make two assumptions. One is that there's a hinge at the center of each beam and column. And the reason why that's accurate is there tends to be a point of inflection where you go from one sign of moment to another sign near the middle of those members. So it's actually not a bad assumption because it kind of happens naturally just in the mechanics of the frame. The second is the shear at the interior columns is twice that of the exterior. And this is related to stiffness of the column based on having a beam on both sides or not, as the case may be. So what I can do is draw something up like this and then say, okay, well, the shear at A, B, and C are all equal, are all related through this 2 times the exterior business. So I can find the shear at the base. Then I can find the shear at the column, which is basically applying the same concept, but just at a different location. And once I know that, I can start a free body diagram of each chunk, kind of like I do in a truss. And if I really wanted to make it quick, I could start up here and say, okay, if I take that as my free body diagram, I have 1, 2, 3, 4 knowns and unknowns. But if I sum moments about here, I can get this vertical in a relationship. Some moments here, I can get that in a relationship. And then I can say summing forces horizontally, that and that and that all play together. Bottom line is I can write a relationship to solve for these 4 unknowns from this free body diagram. Then with that, I can say, okay, what is my moment at point O here? Because that's what I really care the most about. And that's just going to be p sub y times a moment arm of 5 feet in this case. So it turns out to be a really effective method to quickly analyze a big moment frame and just spot check some of my results from an analysis. Additionally, maybe you're in a preliminary design of a building and the architect says, hey, what do you think those column sizes and beam sizes are going to be? In half an hour, you could calculate the basic loads for the building, do a quick portal method, size the member based on these moments and shears, and rather than spending days developing a structural model of this animal, you could quickly, maybe it takes an hour or two, I'm probably being overly optimistic about half an hour, but in a short period of time, you could have a preliminary design of this frame to the point that you could answer the question you were asked, and then down the road, you can do the in-depth engineering analysis and design to get your final drawings put together. All right, so that's looks like all I have for this. Again, the intent, and there's certainly other things, ways to do this. The intent is to find simple hand calc based methods that can approximate finite element solutions or even just complex indeterminate solutions that we may not have the time or the inclination to solve at that moment. All right, good luck with this.